Let's just wait a little for more people to join. Okay, we can start. This is the point at which we had stopped the last time. Now, today's session, I believe this is session 8, is probably going to be the last one for a while, since I'm going to be away for roughly a month. But in between, while I'm gone, I think Shekhar and Nikhil might do one session, and Mihir also may do a session on metrics where um, he will give examples of metrics that we've been using in our various solutions and motivate them in terms of why we're using those metrics. So the whole team will then have an idea of what are the different types of metrics that we use for both for developing the AI as well as for evaluating it. So in the last session, we were talking about we're just in fact halfway through this discussion of PR curves, and one of the things I had mentioned was that um, the prevalence is often easier to calculate than things like sensitivity and specificity. And the reason is that sensitivity, for example, requires all of your data to be labeled before you can calculate it. So remember, sensitivity is the proportion uh, of your actual positives that are predicted to be positive. So you need to know which ones are actual positives in the denominator. Whereas with precision, precision is the proportion of the predicted positives that are actually positive. That means that if you deploy your classifier, all you have to do in order to calculate the precision is that every time your classifier makes a positive prediction, you label that point. So you have to label you label that datum. So you end up labeling far fewer data in order to compute precision than you would in order to compute sensitivity or specificity. So in a practical context, precision is often a metric that we use, and it also gives you a good idea of the accuracy of the classifier because it's really telling you all its predictions, which ones are wrong. Um, so this is another curve that we plot often is a precision recall curve. And precision, as I said the last time, is something that should be compared to the prevalence of the positive label, right? So it's a good model if the precision is significantly higher than the prevalence. Okay, so now let's go ahead and discuss how the operating point is chosen. So if you remember from last time's discussion, an operating point is actually equivalent to choosing some point in ROC space. And once we know the accuracy characteristics of the model in terms of this ROC curve or PR curve, then essentially what it means is choosing a point on one of these curves. So here I've shown you two different ROC curves. This is ROC space with two positive rate of sensitivity on the y-axis and one minus specificity on the x-axis. And the two curves may correspond to two different models. Clearly, the blue model is better than the green model because it's above the green model and it's closer to the top left corner of the diagram. Uh, so the blue model is better in terms of sensitivity and specificity overall. Now um, you can choose an operating point on either one of these curves depending on which model you're deploying. So let's say this green operating point corresponds to a specificity of zero point 0.7, meaning 1 minus specificity of 0.3 and a sensitivity of 0.7. Whereas the blue operating point corresponds to a specificity of zero point 0.7 and a sensitivity of 0.95. Right? So the way one usually talks about operating points in these situations is you keep one metric fixed. So let's say specificity is fixed and the other metric to be larger than a particular value. So for example, in a typical screening solution situation, you might say that my specificity is fixed at 70%, and I want the model to achieve a sensitivity greater than 85%. Now, if you look at the green and blue curves, do either of those two models fit this requirement? It's a question for you. So the requirement again is that you want the model to have more than 85% sensitivity at 70% specificity. Should be obvious, right? Looking at the figure. So the again, the green and the blue curves correspond to two different models, and 70% specificity means that 1 minus specificity is 30% or zero point 0.3. For the green model, at at a specificity of 70%, you have a sensitivity of 70%. So it doesn't satisfy this criterion of greater than 85% sensitivity at 70% specificity. Whereas the blue curve does satisfy that criterion because the sensitivity at 70% specificity is 95%. Right? So, so if this is a condition for deployment, so often conditions for deployment are specified in this way. And then you can look at the curves and immediately decide whether your model satisfies that condition for deployment or not. Yeah, is this clear?
Yes, Albert.
Okay.
Yes.
Now, there's sort of a related topic, which is not, we won't come across this very often, but since we are discussing this whole issue of AI outputting a score at operating point and so on, I thought I should bring it up, which is this topic of model calibration. Um, Now, I've told you that, what do we do with the score of an AI model? Remember, the AI model will typically, let's say it's a classifier, a classification model. It will typically output a risk score, right? And then you have to set an operating point to convert it to a 0, 1 type of classifier, a binary classifier. And when we actually set an operating point, then we can forget about the score, the underlying score. But sometimes, in fact, it's useful to know this score and to interpret it as a probability. So, so for example, especially if it's a risk score, and the risk score is something like 0.65, let's say it's a risk score for a disease, then you might want to interpret that as a probability and say that, does that mean that if my risk score is 0.65, Does that mean that I have a 65% chance of contracting the disease? Right. So it can have a useful interpretation. Now it turns out that in most AI models, a risk score of 0.65 doesn't mean that you have a 65% probability of getting the disease. It just means that you have a higher risk than somebody with a risk score of zero point 0.5 or somebody with a risk score of 0.58, and you have a lower risk than somebody with a risk score of zero point 0.8. The number by itself doesn't really map to a probability as it stands. So what we do often is what we call model calibration, which is that uh, you transform this risk score to a probability. And essentially, what happens, I'm not going to talk about the mathematical aspects of doing this transformation, but essentially um, you ensure that, if your risk score is say 0.65, then you really do have a 65% chance of having that outcome. And the way you ensure it is you have an additional modeling process where you enforce this on the training data. That on the training data, if you have a certain score, then that score maps to the probability. So this is an additional sort of learning process for the AI, the calibration process. But it's a much simpler learning process than the process that led to the risk score in the first place. Okay, and this process is called model calibration. So the use of model calibration is to convert these AI outputs to probabilities. Okay. Now, so far, all that we've been talking about is in the context of classification models, right? I've always taken the example of a classifier, and that too, most of the examples have been uh, that of a binary classifier that takes one of two decisions, right? But there are other types of models, and in fact, in our work, we do look at other types of models like regression models. Now, what is a regression model? A regression model actually predicts a continuous numerical value. It doesn't predict a class value, right? So, for example, in our anthropometry project, the baby weight model is a regression model, right? We are predicting baby weight. We are not predicting whether baby is underweight or overweight. We're just predicting baby weight, the weight itself. And that is a regression model when you actually predict a number, right? And these models, so you don't have to, you don't have to convert these to 0, 1 class models. So you don't have to set an operating point or a threshold or anything like that. You just interpret the predicted value as it is. Right? So if the AI model predicts baby weight to be 1.2 kg, it is 1.2 kg. There's nothing else to be done. Right? So for this reason, regression models are somewhat easier to evaluate than classification models. And what you do is you only need to compute the error between the predicted value and the ground truth value. In fact, we've seen this confusion about what metrics to apply for regression models, even among some of our funders, as Aditya can attest. Uh, they've been asking for things like sensitivity and precision and so on for regression models, for an anthropometry type model, which really doesn't make sense. All that makes sense is a error with respect to the ground truth. And this error can be measured in different ways. So here I've given you two different formula. One is the what is called the L1 error, which is simply you take your predicted value, subtract the ground truth value, take the absolute value, and then average all of those. So it's just the difference between predicted and ground truth, absolute value, and average. Then there is this L2 error, which instead of just taking the difference, you square the difference. I mean, the idea is just to convert all of these errors into positive numbers. So you either take absolute value or square and so on. So a number of metrics like this, but they're generally simpler than the classification metrics. Sometimes it's, so yeah, so what is commonly used are these sort of averages like L1 metric, L2 metric. But instead of using averages, sometimes it's also often useful to know what proportion of your data lies within a certain error range. So again, if you look at the baby weight example, the user might want to ask, Well, okay. So your average error in baby weight is say 120 grams. So that is 120 grams is the average difference between the predicted weight and the actual weight, right? But the average hides a lot of things. I mean, if the average is 120 grams, it could be that some babies have an error of 500 grams, whereas some babies have an error of 10 grams. So it's often useful to know things like what percent of babies would lie between, would have an error of less than 100 grams. And so this is a different way of quoting the same type of error metric. The fundamental error metric is similar. It's an L1 or L2 error typically. So, but you might quote it slightly differently and say 80% of babies in the test set have predicted weight that is less than 150 grams away from the true weight or something like that. Okay, let me pause a bit. Any questions to this point? So basic messages, generally speaking, regression models like this are easier in terms of evaluation. The metrics tend to be simple, whereas classification models, as we've seen earlier, you need to do all this operating point definitions or threshold definitions, create ROC curves or PR curves, and so on. Yes, Ayushi.
Yeah, when would you use one over the other?
Use which one over which
So
one?
like when would you use like a regression model over like a
Okay, so good question. Yeah. So this is actually part of the problem definition itself. What is to be predicted? So in the Anthro case, I don't know if you were around then, but earlier the problem that we were addressing is predicting whether the baby has a weight below 2.5 kg or not, which is a classification model.
Mhm.
But then it turned out that the relevant use case for the kind of work we are doing is not really that. The relevant use case is growth tracking. We want to track the growth of the baby. In order to track the growth of the baby, it's not enough to know whether the baby is just less than 2.5 kg. You need to know its actual weight, right? So then we've converted this to a regression problem because we need to the AI needs to predict its actual weight, not just a class where whether it's less than 2.5 or more than 2.5. So this is part of the initial problem definition that AI and program have to agree on. This basically actually mainly comes from the program team. What is useful to predict in order to create on the ground impact. That is what dictates whether it will turn out to be a classification problem or a regression problem. So for example, in the LFU model, it doesn't make sense to have a regression problem. We're just predicting whether the patient will be lost to follow up, meaning stop treatment within 6 months or not. Now you could, if you had the data for it, you could actually convert it to a type of regression problem where instead of predicting whether the patient will, just disappear within the next 6 months, you could predict after how many months would the patient be lost to follow within 1 month, 2 months, 3 months. So you actually have to predict the number of months. Then it would be a regression type of problem. But that's not the problem of interest for various reasons. Initially, we were thinking about it, but it turns out that the data in Nikshay itself is too noisy for the AI to be able to learn stuff like that.
Okay, yeah. And let's say, I mean, like, how in Answer we pivoted, right? At some point we said that we need to go back and redefine what we're looking for.
Yeah.
Uh, is it typically, I mean, very time consuming to switch or,
Yes.
okay,
Yes, it is. It is. I mean, essentially, you've changed the problem definition.
yeah,
So the AI needs to be retrained completely. There are code changes in the training code. Any optimization you may have done for the previous problem will not work for the new one
okay. So
at a code level.
kind
Yeah,
of starting from step one where you've collected the data and now
yeah.
you're
Yeah,
preparing.
it's all yeah, almost like starting from scratch. Yes. Yeah.
Cool. Nice.
Aditya.
Yeah. Just a question which had come up when we were engaging with some of the funders, and my concepts are not very clear on this. So
Hmm.
they had said that, let's say, in the case of newborn anthropometry, did we use other methods like coefficient of variation and paired t-tests? Would that be relevant in the context of the anthropometry performance? looking at those kinds
No,
of methods?
no, these are mostly statistical methods that actually have, at their heart, they have a sort of linearity assumption. They assume that there is a linear relationship between the outcome and the features,
Mhm.
which is not true in most of our cases. So they're usually not relevant.
Right, right. Okay.
Any other questions? Okay, let's do a little recap on all this, operating points and metrics and so on. We started with accuracy, sensitivity, specificity, etc. And I mentioned that these all of these metrics are different aspects. They expose um, different types of behavior of the model or different aspects of the accuracy of a classification model. Right? None of them individually provide a complete picture. The complete picture is provided by the confusion matrix because that tells you true positives, true negatives, false negatives. From that, you can calculate all of these other metrics, right? Now, the problem with AI is that the confusion matrix itself relies on choosing an operating point because the AI will output a score, not a 0, 1 classification, right? This is something we had also discussed. So you first have to decide on an operating point that converts the classifier output from a numerical score to a class prediction by thresholding the score, right? Obviously this is not done for regression models, only for classification models. Then we discuss calibration. The numerical score sometimes needs to be directly interpreted as a probability. In such cases, you have to do some additional work to convert the score to a probability, and this additional work is called calibration. Then we say that the AI model output is calibrated. We talked about ROC space and PR space as two spaces in which one can visualize operating points and also metrics. Uh, and the overall performance of a classification model can be visualized by a ROC curve or a PR curve. And we also talked a little bit about the area under these curves being an overall measure of the accuracy of the model in sort of a way that is independent of whatever operating point you choose. So these curves do not depend on choice of operating point since they actually correspond to a whole set of operating points. In order to draw the curve, you have to compute the confusion matrix at every operating point. Um, but once you've drawn the curve, then the curves are often used to select an operating point for the model. It's very easy once you have these ROC curves, then given on the ground criteria on things like sensitivity, specificities, on the ground requirements, or precision, and so on, you can just eyeball the curve and decide what should your operating point be. Uh, we also discussed that the ROC curve should lie above the 45-degree line, which would correspond to a random classifier. And similarly, the PR curve should lie above the horizontal line corresponding to the prevalence, which is also what a random classifier would output. And generally, the higher these curves are, the better the model is. That's the overall interpretation. Okay.
Alpan, these
Yeah.
so just to recap, the curves, these ROC curves, these are only for binary classifier.
Binary classifiers. That's right. Absolutely. Even for a multi-class classifier, it gets very complicated.
Right.
Because when you have multi-class classification, then you don't have a single sensitivity or a single specificity. For each class, you have a different sensitivity and specificity. And then people talk about ROC surfaces in three-dimensional space and all that, but they're very difficult to visualize and interpret. So multi-class classification, I didn't want to address it here, but it comes with its own sort of can of worms. The metrics tend to be a little more complicated in multi-class classification.
So just does that affect then our choice of sort of problem framing that you don't
No,
want to go down
no,
that
no,
route?
no. No, no, no. We have that possibility. I mean, for the teleradiology project, in fact, we are doing multi-class models. And we can compute sensitivity, specificity for each class separately.
Mhm.
It's just that you can't visualize easily with these ROC curves. I mean, if you really want to, you can even do that where, let's say you're trying to predict one of many classes, then, and let's say you first one by one select which class is of interest, right? So, for example, in teleradiology, we have 14, something like 14 different features that we are trying to predict in an X-ray. And let's say you focus on one feature, then you can also convert it to a binary classification problem by saying anything that is classified as this one feature is what I call a positive. Anything that's classified to any other feature, I call a negative.
Mhm.
So you've converted it to a two class or binary problem, and then you can do all this ROC analysis. Then you go to the next feature and treat it the same way. Say this feature is my positive now, everything else is negative. And then you draw another type of ROC curve corresponding to the second feature, and so on.
Right.
So it doesn't, I mean, the fact that it gets complicated is not a hindrance to us working on multi-class problems. I mean,
Okay.
we do it all the time. In fact, what we work on should simply be dictated by what is useful on the ground.
Okay.
There are no technical issues as such. Okay, so I think this completes our intro to evaluation. And so this is sort of the last section, which is deployment considerations for AI models. And so I think today we actually might be done before time. Let's see. There's not that much material here. Um, so so let's say we built an AI model. We've done all these evaluations in terms of ROC curves, PR curves. We chose an operating point. We think at the operating point the performance is satisfactory. Or we have a regression model and we've computed the L1 error or L2 error or something like that. And we find again that is low enough so that the performance is satisfactory and we are ready to deploy. So a typical step that we would like to do before deployment is something called passive evaluation of the model. This is something we did in LFU. Um, what this means, a passive evaluation, it's an evaluation of the AI model in an environment that is as close to the real world as possible. So you want to simulate a real world situation, but at the same time, since you're still in evaluation mode, you're actually not using the model, no action should be taken basis the output of the AI. So you just record the output and use the output in order to evaluate what is the performance of the model in a real world situation. And this can be done in various ways. So one example is that you remember I talked about data splits and one of the things that I'd mentioned there was creating a longitudinal split of the data where the training data consists of um, consists of data from a certain time period, and the test data consists of data from a later time period. Right. So this is a longitudinal split of the data. And the reason this is useful is because this corresponds to a real world situation. In the real world, when you deploy an AI model, it will always have been trained on data from the past and it's being applied to data in the future. So the real world situation comes close to a longitudinal split. And this is why we want to evaluate the model in the context of a longitudinal split. Um, and this is a passive evaluation. Similarly, the other thing you could do is actually integrate the model into a software system, but the model output should be logged in the backend and not exposed to the user. This would also be a passive evaluation. You're not exposing the output to the user, just logging it in the backend. And you also need to be able to measure the ground truth at the same time so that you can evaluate the model output. So the second situation would be called more like a passive deployment rather than a passive evaluation. But they're both passive in the sense that there is no decision taken basis the output of the AI. So you're not actually using the AI, you're simply evaluating it. Okay. In general, I would say a passive evaluation must be done prior to deployment. I mean, we've violated this sometimes in some projects, but really this should be the norm. I mean, this is sort of healthy a healthy way to develop AI models. Just like over the course of time, if you look at software engineering is a fairly mature field in comparison to AI, which is more recent. And there are basic sort of software engineering principles that have developed over time. For example, having unit tests in code, having code reviews, and so on. And this is something you typically don't compromise on because you don't want to, you don't want the software system to have bugs, which could have been fixed very easily if you had these processes in place. So similarly for AI models, some of these sort of best practices are still being developed, and in our context, a lot of it is still new because we are working in a very new type of space as far as AI is concerned, and so we're still developing some of these best practices. But I think one of the um, one of the processes that we should include in our best practices is to always have a passive evaluation or a passive deployment prior to a real world deployment. So I would actually strongly discourage a direct deployment in which the model output is just exposed to user directly after some internal tests have been done. It should be a gradual process. It's not a good practice in applied AI work. The reason for this is the passive evaluation provides yet another opportunity to tweak the model if the behavior is at odds with what you found in internal tests. Right? And this can happen. This can happen for a number of reasons. Um, Actually, let me ask the audience, right? Just based on everything we've discussed and talked about so far, under what situations can this happen? That let's say you have an AI model in internal tests, it does well, but then when you deploy it in a passive evaluation mode, it actually doesn't do very well. Why would that happen? Any ideas? Yes. Sorry, let me just check. Yeah, Deepashri. Yes.
So, based on what we've learned in teleradiology, if you've trained your model on a data set that was procured from like another country,
Yes.
from a different race, and then you deploy it in India, and
Yes.
the data points would differ. Like the model would not recognize certain features in,
Correct.
let's say, chest X-rays, to be more
Yes.
precise, more accurately in the Indian population, may miss out certain features.
Yes.
Yeah.
Absolutely right. Yes. So that is one example. Um, would it be possible that you would actually train the model on India data and still this happens?
Um, it would, right? So I think this came up uh, in the workshop that if
Hmm.
you train the model without passive deployment, which is I think what we're doing right now,
Yeah.
the model can influence the behavior of radiologists and
Uh,
override that,
yeah.
or the radiologist, if they don't have enough trust in the model, they may dismiss the model's finding,
Hmm. Hmm.
uh, against, with personal bias. So that can also happen.
Yeah, but they see that would be a situation where the label is changing, right? The label acquires a bias, and therefore the model appears to be not doing well. But actually, it could be doing well. It's just that the radiologist is biased, right?
Right.
But my question is slightly different. I'm asking, is it possible that the model by itself doesn't do well, even though it's been trained on India data? Sorry, um,
I think
Kaushik.
also.
Yeah.
It could be possible because he might not have considered a representative
Yes. Exactly.
sample.
Exactly. When you train the model, you might not have taken a representative sample. You might have gotten some special access to data and trained it on that data to which you had access to, which may not be a representative sample. And therefore, when you actually deploy it in a real world situation, it doesn't do as well as you expected it to. Aditya?
Could it be also that the feature set or the feature list is not as complete as it should be, or there may be more things that in the
Yeah,
same.
but that's possible. But usually, you would have then already encountered red flags while you were doing internal testing.
Alpan,
Remember a term that I've used to discuss things, discuss situations where there's something different about the data on which you train the model and the data in the real world environment. What was the term that I used? Anybody remember? Yes, Deepashri.
I don't remember the term, but I had another question.
Sure.
So if you deploy the model and the data inputs that it gets, like the chest X-ray, let's say at a health and wellness center,
Hmm.
they are not in the correct data format, as in if they are like
Yeah. So,
it's
yeah,
not-
there are format differences.
yeah,
Yes.
that could
Format
also,
differences in the data would be a bug, essentially.
so
But
not the
yeah,
model's fault.
not the model's fault. But I had mentioned a term early on. Remember a term called data drift?
Yes.
So that's the most common cause of this difference. So the model, and in fact, data drift encapsulates many of the things that you already mentioned in your answers: the lack of representation, data from another country, and so on. All of this comes under data drift. What data drift simply means that your deployment environment, in terms of the characteristics of the data, has fundamentally changed with respect to the characteristics of the data on which the model was trained. Right? It's like suppose you've trained a robot to navigate mazes, and all its life, life in quotes, all its life, the robot has only seen green mazes, and then suddenly you put it in a blue maze and it goes berserk. There's a data drift because the environment has changed, and the robot no longer recognizes the environment and makes all kinds of mistakes. The similar thing is happening with the AI. And that is why it's important to do a passive deployment to detect problems like this before we actually use the model. It doesn't mean it completely mitigates the risk of a real world deployment, but it reduces it drastically. Yes, Aditya.
So, could you give an example of a passive deployment? Like, would that mean that it would, let's say, go from the lab onto a smartphone?
No, so as I said, there's two types of passive evaluation. One is just an evaluation without a deployment. That's the sort of first bullet point there, where you just create a longitudinal split of the data, which is what we did in our LFU project. So
Right.
as we were initially experimenting with our LFU model, we had initially evaluated it on a random set of data points, and we got a certain accuracy. But then we said, well, we don't know if this accuracy will actually reflect real world accuracy. So let's do a passive evaluation. And we spent a lot of time designing the passive evaluation. If Mihir is in the audience, he can attest to that. There was a lot of effort that went into designing it to make sure that the test data was separated in time from the training data, number one. Number two, the test data was representative in terms of the districts across the country, that there were enough people from every district represented in the test data so that we didn't see biases and so on. And then the model was evaluated on that. And sure enough, we found that when you do a passive evaluation as opposed to the earlier evaluations that were going on, we saw a small dip in accuracy. And that really means that when a model is trained on older data, the characteristics of the newer data have changed somewhat, and that is showing in that accuracy dip. Fortunately, the accuracy is still high enough for the model to be deployable and usable, and we've done a number of passive evaluations since. So this is an example of. I don't know if this answers your question, Aditya.
It does. It does.
Okay. Okay, let's push ahead. So I'm sort of, maybe I interchange the two slides. So let me just remind people what a deployment is. We've talked about passive deployment and passive evaluation, but true deployment is essentially the integration of an AI model into a software system so that it can carry out inference on the features that are fed into the model. This is sort of a recap. I'd already mentioned this probably in session one, that this is what we mean by deployment. The difference between inference and deployment is inference is just a model acting on some test data and producing an output, whereas deployment is the model is integrated into a software system. The software system could be a cloud-based system, it could be an app, and the hallmark of a deployment, the distinguishing feature is that it typically represents the first time that the model will be used by people outside the team that built it. Right, so this it represents deployment represents a major milestone in the AI development process, and for this reason, uh, deployment should not be done without proper testing and checks and so on. Okay, Mihir, sorry, I can't read what you.
Oh, just a addendum to what you mentioned about the diffuse passive evaluation. Not a question.
Okay. Now, one of the things that everybody in our team should be very clear about, and with regards to AI deployments, is that there's a fundamental difference between AI deployment and other types of software deployment, which is that AI deployment is a continuous process. The reason it's a continuous process is this very issue of data drift. Data will always drift, meaning data today will not look the same, and even data, with reference to the same situation or in the same context today will not look the same as data 10 years hence or even 2 years hence. Right? So the characteristics of data are constantly changing, and therefore your deployed AI model needs to be constantly retrained. In software, in standard software development, you may release different versions of a software product, but the versions typically differ in the sense that you may add more features. Right? When you when you have sort of an Android OS update, the new OS probably resolves bugs in the old OS, adds additional features, and so on. There's some extra stuff. Some bad stuff is removed from the old OS. Some new stuff is added. It's like that. In an AI model, even without adding any new functionality to the model, you still have to keep retraining, you still have to keep redeploying simply because the underlying data has changed. And this is sort of a fundamental difference between a standard software product and an AI product. Okay. So this is just sort of a diagram that explains part of what I've been talking about. So you've seen this diagram before from session 1, where you have raw data. Raw data goes through this process of sampling, cleaning, transformation, annotation, and so on. At the end of that, you get data plus labels. Data plus labels are fed into an AI algorithm. Don't worry about metadata and augmented data and so on. But essentially, data plus label are fed into an AI algorithm. AI algorithm goes through a training process where it learns to map the data to the label, and that output of that training process is an AI model. An AI model is then deployed. So it acts on new data and predicts a label for the new data. Now, what this oval represents here is the fact that the data on which the AI was trained and the data on which the AI will be deployed have to come from the same environment for the AI model to work. If this data is from a very different environment than that data, the AI model typically will not work well. Yeah. So, yes, Aditya.
Sorry, just to be clear, when you say environment, does that mean it has to be the same? Let's say if it's
Yeah, I'm using a loose word. Yeah.
right. Okay.
It has to have the same characteristics mathematically. So similar, what we say, I talked about data distributions. If you
Right.
remember earlier, the distribution should be similar.
Right.
And that typically will happen if it's similar environment. If the environment changes, the distributions also change.
Mhm. Okay.
And this is, this is actually saying this is, same thing in a different way. You have this gray oval that represents a single environment. Your training data comes from that. So this environment is what I call the deployment environment. Training data comes from that environment. Inference data also comes from the same environment. Inference data is fed into the deployed model, resulting in a prediction. And to go from here to there, there's this whole process, internal process that we go through, that the AIML team does, which is data processing, annotation, featureization, AI model training, building process, in order to go from training data to a deployed model. Yeah, so ideally, you want both of these to come from the same environment. Then I spoke about data drift earlier, and data drift is when you're uh, one sort of very common example of data drift, meaning change in environment, happens just as a consequence of time. So with time, what can often happen is that your inference data or your entire deployment environment becomes different from your original training data environment. And that is what we call data drift. And in such situations, the model is not expected to work well anymore. Okay, the data is sort of drifted away from the original uh, uh, sort of training data characteristics. Okay, there's a related concept. Many of these concepts are sort of very tied together, passive deployment, early deployment, and so on. So I just want to make sure you understand all of these different concepts, and they have overlaps. Um, so sometimes it happens that a model is not fully production ready, or that we don't have enough data to get it to that point of being fully production ready, where we can't even properly evaluate the model. Case in point is our CUF project, where we are developing a screening tool for TB using CUF. We don't have currently we don't have the data to even evaluate even though we have an initial model, we don't have the data to even evaluate it as a screening tool because we don't have enough data from the community setting. A screening tool is used in a community setting, right? Not in a hospital setting. Our AI was trained from data in a hospital setting. And similar issues with Anthro, right? It's just now that we are beginning to get community data. But for a long time, we were in a state where we only had data from a hospital setting. So we were not even in a position to evaluate the AI in a real setting, in the setting that it's meant to be used. And in such cases, it is actually I should change the word often to sometimes. It is sometimes useful to carry out an early deployment, not often. Yes, Aditya.
In the case of the cough for TB, so a cough sample from a facility versus a community,
Yeah.
It's primarily the background noise that would be different?
No.
Okay.
No, so the facility is all the people who are coughing in a facility are people who have health-seeking behavior. So
Right.
there's something wrong with them, which is why they're in a facility.
Right.
So the AI has never seen perfectly normal subjects, which is
Right.
what you would see in a community setting, and they could have different characteristics of cough sounds.
Okay.
Yeah. Yeah. So in cases like this, it's sometimes useful to carry out an early deployment. Early deployment should be passive because the model is just not ready yet, right? So it's definitely a passive deployment. Model should not be used as a production model, and on the ground action should not be dictated by its outputs. All the characteristics of a passive deployment. There are two main purposes to this kind of deployment, right? One is that you may have some sort of model that you are not sure about uh, in the lab. You've never had a chance to really evaluate it. It's sitting there. And so the early deployment would be a means to evaluate it in a real world setting. So it's sort of, in that sense, an early deployment is like a passive evaluation because you're deploying it at the same time you're collecting the ground truth label through the deployment. So you have an opportunity to evaluate the model. The second use of an early deployment is actually to collect more data. So the nice thing, see, the moment you evaluate an AI model, what are you doing? Your AI model is producing an output, right? To evaluate the output, you also have to know the ground truth. Otherwise, you can't evaluate the output. Now, the moment you know the ground truth, you've created an additional training data point for the AI. So every evaluation is also collecting additional labeled data for you. And this is the advantage of a passive evaluation or an early deployment, is it's a means of collecting additional labeled data through the evaluation process. So for example, we are planning this DLSS. I don't remember the full form of the acronym, but it's a survey, it's a community based survey for the CUF solution, which will be an early deployment. And there we will be collecting additional data as well as evaluating our existing model at the same time. Now, there's one thing to understand is that this method of collecting additional data through evaluation is not just a hallmark of early deployment. Even when you have a late stage deployment, when you have a finished, quote unquote, finished model, an AI model is never finished, but say you have a reasonably mature model, which you put in production, you always want to keep evaluating the AI for the reason that we've talked about, right? Because of data drift, issues like that. You never want to be in a situation where the AI is not being evaluated. And so whenever you are evaluating AI, you are automatically collecting additional training data. And you can feed that back into the AI model to make it better. Right? So this is like a hallmark of all AI deployments is that you will have continuous evaluation going on. Continuous evaluation will create more training data that will feed into the next version of the AI model. Is this clear?
So, Alpan, early deployment and passive deployment are
Very similar. Very similar.
okay, similar, not same.
Yeah. Well, uh, I mean, you could. It's just there's a slight difference, which is that a passive deployment can happen anytime. A passive deployment is just deciding not to take action. Say you have a certain version of the model and you want to deploy without taking action basis the output of the model, then that's a passive deployment. It can happen at any stage,
Mhm.
right? And early deployment is just something that's early in the history of the development cycle.
Right. Yeah. Because I mean, very often in projects we hear both of these terms being used, and we're
Yeah,
often
yeah, they're very similar. Yeah.
what and passive evaluation, passive deployment are the same.
No,
No.
no. So I mean, again, this is not stand. I should warn everybody. This is not standard terminology. This is terminology I have sort of created to make it easier for us to separate out these concepts. Uh, so what I mean by passive evaluation is something like what we did in the LFU project, where we just evaluate it on a longitudinal split of the data without actually deploying the model. So we haven't integrated the model into Nixshay or any app or any software system, anything like that. It's still internal. Whereas a passive deployment would be an actual integration into a software system.
Okay. Okay. Yeah.
Yeah.
So would you also say that passive deployment then is a good opportunity to also learn a
Yeah.
few user related like metrics as
Yes,
well?
absolutely, absolutely. You could add all of that in because it's a golden opportunity for testing the whole system in a real world setting without the risk of it. Since you're not actually using the system, there's no risk, right?
Right. Right. Okay. Thanks.
Yeah. And there's yet another term which I haven't really introduced yet, which is adoption. Again, I think they're more relevant to our space. So there's evaluation, there's deployment, and then there's adoption. So you could have AI model deployed, meaning integrated into a software system, but nobody may use it. Right? It's there, it's sitting there for people to use, but nobody may be using it. And when people actually start using it uh, at some scale, then we can call that adoption. Again, these are concepts that I'm sort of inventing, but I think it's useful to have some of these uh, concepts into sort of ingrained into our common thinking. Okay. Where was I? Yes. So now we come to the post-deployment phase, which is M&E. And M&E is one of the most important components of AI. Um, even more than a standard software product, an AI product has to be monitored and evaluated at a much more detailed level, at a much higher frequency than a software product. Simply because an AI model is inherently brittle. It's very dependent on data. And the moment you have a data drift, its performance can dip. So you have to monitor it continuously, right? It's not like any other piece of software. Um, so the way you monitor it, you have to by continuously. I don't mean like every day or anything like that, but at least periodically evaluate. You must evaluate the accuracy of the model at periodic intervals through annotation of data, right? And you don't have to annotate all your data, otherwise the model would be useless if you had to annotate everything. You won't need to use AI. But you should judiciously, there are ways of judiciously choosing a sample of the data, annotating that data, labeling it, and knowing the output of the AI on that data, and then comparing the two to evaluate the model. Right? And this has to be done in a fairly continuous fashion. And we have to develop systems to do this, which we don't have in our organization as yet. Right. So this is something we really need to set up. Now, as you are evaluating a model, what will happen is that at some point the accuracy, this always happens, by the way, no matter how good the model is, at some point the accuracy will dip below expectation. And then you need to have systems to diagnose why is this happening? Why is the accuracy gone down? Is it because of data drift? Is there some kind of software bug? Did somebody release a new version of the app or the deployment software? And that has resulted in a bug. It's not reading the data correctly. It's not doing inference correctly. We need to diagnose all of these things, right? And then once you've diagnosed it, let's say you don't have any other bugs, and it's really a consequence of data drift. You have to retrain on new data as necessary, and you can only get new data if you've been evaluating, right? If you've been evaluating, then you have labels for the new data, and you can integrate that into the model and improve it. So this is sort of a continuous process, right? Monitor accuracy. Accuracy will dip at some point. Use fresh data to retrain the model. Again, the accuracy goes up. Keep monitoring again. Monitoring will generate more data, more labeled data. Accuracy will dip. Add the new labeled data to the model, retrain it again. This is sort of a continuous process. And we have to, from the engineering perspective, we have to be able to automate these processes. If we are not making any other fundamental changes to the AI algorithm, if it's just a matter of retraining, we should be able to automate this whole system so that it's almost push button. I mean, this is what happens at big tech companies, is that there's continuous evaluation going on of deployed AI models. You can actually see various metrics on a dashboard. The moment you see certain critical metrics dip in value, an alert is sent to the appropriate person. This person will then look at the dashboard, press a button to select fresh data to retrain the model. It's all like one or two clicks, right? Confirm the data selection, add that data to the training set, retrain the model. That's another click. And then evaluate the retrained model on the new data. And then okay the retrained model and deploy it. Right? So all of this should be doable. In fact, in most of the big tech companies, this is doable through a few clicks. We need to be able to get there. I think for us, the retraining cycle will not be that rapid, I hope. I used to, at one point when I was working at Amazon, the models I was developing would have a lifetime of just roughly a week. So within a week, you would start seeing dips in accuracy, and they had to be retrained every week. And you can't do that manually. It's an automatic process. In our case, I think our models will at least have a lifetime of a few months, I hope. Um, so this is the iterative nature of AI, right? Deployment, monitoring and evaluation, uh, fresh data integration, retraining, deployment. Again, the cycle repeats, right? And what I want to say is also that it's not always necessary in this cycle to improve your model, to improve the AI algorithm. All you have to do is supply it with fresh data. You can think of it as a dragon that's constantly consuming data, right, in order to stay alive. So, in most cases, you can solve this accuracy dip issue by simple retraining on new data. In some cases, when you can't solve it by retraining on new data, then then that's a signal of a concept drift, meaning the mapping from your features to your labels. There's something fundamental about the mapping that has changed. And so then you need to look at your features again. You start developing a new version of the AI, a new algorithm, right? And that takes more time. So, so often we distinguish between model refresh. Refresh means that you're just retraining the same algorithm with new data versus model version, uh, which is where you're actually using a new model or a new algorithm. Okay, questions? Okay, and this I think is the last deployment topic that I want to discuss, which is human in the loop. And all of you, I think, are familiar with this in some form or the other. We've been using it, for example, in the LPA project. Um, so the idea of human in the loop is really a means to uh, the human using human as a means to uh, control the performance of the AI, to make sure that the AI doesn't take uh, decisions that can have dangerous consequences. Um, and one way to do it is for the human to control the low confidence decisions of the AI. So let's say if the AI outputs a high score for high risk score, it typically implies greater confidence in that label, whereas low scores indicate low confidence. So one of the things you can do is you can increase the accuracy of an AI model by simply taking all the data with low scores and getting them annotated by humans. So having the humans decide instead of the AI decide. So you're still not you're not the AI is not ceding all authority to humans. If it were to cede all authority, then you wouldn't need the AI model. But at the same time, the human has some control over the AI, and therefore the human plus AI as a unit has improved accuracy over either actually over the original AI system. Right. So this process of sending low scoring data for human annotation is called human in the loop. And there are many ways to optimize the use of human in the loop. Obviously, we want to achieve a certain accuracy or a certain level of fairness in the AI uh, by using as little human resource as possible. And this becomes an optimization problem that one can solve in various ways. And so essentially, you have this process where a human is rechecking some sample of the predicted AI labels. And so this type of process is termed as human in the loop. Um, Now you can do this in an iterative fashion. So if the human in the loop annotations, let's say your AI is confident about certain decisions, and those decisions you don't question, whereas it has low confidence about other decisions, and for those other decisions, you have a human sort of labeling that decision. Now, so when these sort of labeled decisions are fed back to retrain the AI in an iterative manner, this process is called active learning because it's learning in the presence of a human, where the human labels some data that gets added to the AI gets retrained, produces new predictions. Some of those predictions are again labeled by the human, again that gets added to the AI, and so on. And this happens in an iterative manner. So this process is called active learning. Right? Um, if all the data is rechecked by a human, then that sort of defeats the purpose of the AI, right? Is it really? So we really have to evaluate, why exactly do we have an AI model deployed if it is always rechecked by human? Uh, and in fact, it may make sense in many situations. So, for example, in teleradiology, or where you have a critical health decision to be taken, this is the outcome. You might want every single prediction of the AI to be rechecked by a human. So then you can ask, what is the use of the AI? Why do we have AI there? Well, maybe the AI makes human decision making faster because the human can use AI as a tool or as an aid, right? Just like they use any other technology. By human here, in this specific example, I really mean a qualified physician, qualified doctor. The AI could also improve the accuracy of the human in these situations. Okay, so I think we end there for today with the recap. Um, so we've sort of discussed these various concepts. Deployment, as you know, is integration of AI into a software system. It's an important milestone in AI model development because it's sort of a point at which the model is deemed to be ready to use by someone outside the team that built it. Right? Passive evaluation, passive deployment, we've discussed ad nauseum. We've discussed monitoring and evaluation, very important, much more important than in other software products to monitor and evaluate AI products. Data drift also needs to be monitored. And this tells us if the AI model needs to be retrained with fresh recent data, right, which is obtained via the evaluation process typically. Human in the loop is a great way to reduce model errors and biases. The trade-off is that part of the purpose of the AI, which is automating human decision making, is lost in the process. So you really have to balance this trade-off: how much human in the loop versus how much decision making uh, should be given to the AI, and why. So these are questions that need to be considered uh, when you think about human in the loop. So I think, yeah, I won't go there. Yeah. So I think I'll end here today and take questions. There's a last section in this presentation which is really about how we work, meaning what the different roles in our team are, what are people expected to do, and so on. And I think that section, it would be good if Shekhar and Nikhil take it at some point in the next couple of weeks or so. Also, as I mentioned earlier, Mihir, if you're comfortable with it, if you can do a session on metrics for the team, where just exposing them to all the different metrics that we are using currently in our projects.
Sure, bro. I'll do that sometime in the next couple of weeks.
Sure. Yeah, that's fine. So, yeah, any questions?
Alpan,
Yes, Aditya.
recently, been getting a lot of questions about before a project starts, which algorithm will we select? And it seems like a lot of people who may not be that familiar with AI look at algorithms as almost like off-the-shelf products, other like sort of general, libraries of software or whatever that are available. So what would be a good way to generally think about selecting algorithms, and if you could just I mean, are there some that are better suited for some things than others?
So there are, I mean, see, there are general guidelines in terms of if you're doing a computer vision problem, for example, typically you would choose a deep learning model. Now, a deep learning model is not one algorithm. There's literally thousands of different deep learning models.
Right.
And which particular deep learning architecture you choose and so on is really a function of the experience of the AI scientist, intuition. They will try, and even with that, they have to try 100 different things to see what works.
Right.
So you just can't choose a single algorithm in the beginning. In
Right.
fact, if anybody if anybody interviews for our team and says that if we were to give that person a problem, and we do this in our interviews, right? We give them a real world problem and ask them, what do you think? What should you try? here?"
Mhm.
And if they say just use this algorithm, typically they would fail the interview. We wouldn't take them.
Right.
It's just not possible. You have to. I mean, currently the whole field is so empirical. There are no prescriptions for if this do that.
Mhm.
There's no prescriptions like that. I mean, very general. Um, like it's been shown recently that if you're doing NLP type applications, then one of the transformer models might work. Now again, transformer is not one algorithm.
Mhm.
There are many different transformer architectures, transformer models, and you really have to choose what could be appropriate. That will fail, then you have to choose something else, try something else. I mean, this is why the modeling process takes time. Really, it's not the time to run one algorithm. It's really this whole experimentation soup in which you choose, play around with different things to see what works. Essentially, you're tinkering.
Mhm.
Uh,
Right.
and
Okay.
it's the field is still in that phase. I mean, it's not. I don't know if it will ever come out of that phase where you really have just one thing that works for one type of problem. Maybe it will, but we are far away from that at this point.
Okay.
Is there a question on chat? Just checking. No. Okay. Any other questions? If not, then I'll stop sharing. And thank you.
Thanks, Alpan.
Yeah. No. Thank you.
Thanks
Yeah.
very much.
Thank you
Great
so much, Alpan.
session.
I
Thank
hope you
you.
got something out of this. If there's more material, I think I'm actually gone for about a month, so we can, depending on the feedback, I think Nikhil is going to take some, is going to do some surveys, and depending on the feedback, we might decide to add some more material. Uh, we really want this to be a standard training session for anybody who comes into the organization. And I know that certain things I've gone through quite fast without giving too many examples and so on. So we'll iterate on this and improve it. But hopefully it was still useful.
It was very helpful.
Yeah, extremely.
Great.
Thanks so much,
Thank you.
Alpan.
Thank you.
Thank you.
Thank you.
Bye.
Bye.